Okay, so that's the schedule here that we have right now. We are going to look into the electromagnetic waves today. And we're doing this, we're going to do this lab, so-called lab, right? Virtual lab. We finish waves 2, and whatever concept we used in waves 1 and 2, we're going to use also here in this chapter on electromagnetic waves, chapter 33 in the book. And we're going to be using Maxwell's equations here to get the electromagnetic wave. Okay, to explain the phenomenon of electromagnetic wave. It was a major accomplishment to recognize that we do have electromagnetic waves. It was, people start to have some ideas about electromagnetic wave back in the first half of the 1800s. And by the mid 1800s, 1850, 1860, a scientist called Hertz, William Hertz, demonstrated the existence of electromagnetic waves. First, there were theoretical results. No, theoretical results usually precede experimental results, and then Hertz himself demonstrated the existence of electromagnetic waves in an experimental fashion. It was very well sought experiments. It's amazing when we read the history behind that. You know, if you go, Wikipedia has a very nice article. Let me get here. Hertz, William Hertz. Let's see, Hertz. No, it's not this type of Hertz. German guy. If there was a Nobel Prize at that time that he demonstrated this, the existence of electromagnetic waves, most likely he would have won a Nobel Prize for this experiment. I believe it's yeah, that's okay. So we're gonna see. I think it will. Oh yeah, here you go. Wilhelm Hertz. No, he's not a writer. He's a scientist. Let's see. Electromagnetic wave. Let's take a look here. Electromagnetic waves. Hertz. Okay, Hertz experiment. Electromagnetic waves, Hertz experiment. Here you go. Okay, so here you go. I like the article in the Wikipedia. It shows the step-by-step, all the steps that Hertz himself underwent. So why don't we have here Wikipedia? Heinrich Hertz, it's not Wilhelm, it's Heinrich Hertz. Okay, so that's his name. Here you go. That's the guy that demonstrated the existence of electromagnetic waves. Okay, it was James Clerk Maxwell that managed to come up with the equations of electromagnetism that predicted the existence of electromagnetic waves, but this guy was not able to demonstrate in practice its existence. It took Heinrich Hertz to do that, as a German physicist who first conclusively proved the existence of electromagnetic waves. It was a very, smart experiment that he undertook. Here you go. And diagnosed the infection, migraine. Oh, he's dead, right? In 1892. Okay, but I don't want to talk about his death. I want to talk about his experiments on electromagnetic waves. Here you go. Okay, so here you go. We have what we call the transmitter, the generator of electromagnetic waves. Note that we do have a power source here. This is a battery. Okay. And we have a coil here, another coil. What we have here is actually a transformer. Okay, here you go. We have a capacitor here as well. Spark gap. And then we have two metallic spheres with a very small gap between them. Okay. Basically, one becomes positively charged, and the other becomes negatively charged. With this setup allows you to do that. With this small gap, you know, we create an electric field here in between. Okay, and this electric field varies in time and produces an electromagnetic wave. Okay, that's just half of the experiment. That's what we call the transmitter. Okay. So remember this single, 1887. Okay, the late 1800s, second half of the 1800s. Okay, the idea came up in 1879. During Hertz's studies in 1879, Helmholtz, another famous scientist, suggested that Hertz's doctoral dissertation be on testing Maxwell's theory. So it was a PhD thesis of Hertz himself. Okay, it was a PhD thesis, and then what he did in the other side of the room, he put this other circuit that was the receiver, transmitter and receiver, right? No power whatsoever. You don't see any power source whatsoever. It's just the law of induction that we have seen before. Okay. Okay, but Robert here is, I'm practicing here, Robert. Circuit, right? Circuit. Robert is picking up on me since the beginning of the course. Okay, so here goes circuit, right? So here go. We have this electromagnetic wave being generated here at the source. Okay. And it is inducing a current in the receiver that you see right in here. Okay. If you have a magnemeter, you can measure the current flowing through the circuit. Okay. But then he went further. He went further than that. Okay. Why did he put those two little spheres here with a gap? There was a reason for that. Okay. It was not enough for the scientists to show that there was a current flowing along this receiver here. There was not enough. For you to convince your peers, you also have to figure out a way to see what is happening in the circuit, to visualize it. Okay, to visualize it. And then why did he put those two little spheres here? Well, because when those spheres becomes electrically charged, as the electric field becomes stronger and stronger between those two, you can see a spark flying between each of those devices. So that was the way that Hertz himself figured out to show his peers visually, right? Not just by an instrument that measures current, but to show to his peers visually that there was an electromagnetic wave interacting with this circuit that was far away. Okay, there was a spark right in here that was generating an electromagnetic wave, and this spark was also being observed right in here, although not as intense as the other one, right? But it was also being observed right here. And don't forget, this receiver didn't have any power source whatsoever. So the only way that there was a spark being generated right here was due to the circuit here on the left side. Okay. So 1887, that was the apparatus, a spark gap transmitter. That's the transmitter, that's the receiver. Okay. This transmitter here is considered a dipole antenna. Why a dipole antenna? Because, you know, one end here of this device is positively charged, and the other one would be negatively charged. So it behaves like a dipole, electric dipole. Okay, it can be, one can be positively charged, the other negatively charged, and can be the inverse too. Okay, can be the inverse as well. That's what we call a dipole antenna, because it's you have opposite charges at each of those spheres. In addition to dipole antennas, there is also in addition to electric dipole antennas, there is also magnetic dipole antennas, which is nothing but a circle, right? A loop producing a magnetic field. Okay, so here, you know, if you want to read that, it's a really nice story. You know, Hertz himself did several experiments in several different ways. He wanted to know if he could shield the propagation of this electromagnetic wave. Okay, you want to know that stuff, and then he went a step further. He also started to illuminate those electric dipoles with different light sources. One of them, it was the UV source. And he noticed that by illuminating either dipole here with a UV light source, he noticed that the sparks would get stronger and stronger. Okay? And that was the beginning of what we call today the photoelectric effect. In a way, Hertz himself discovered the photoelectric effect. Not only he demonstrated the existence of electromagnetic waves, you know, that's the breadth and depth of his contribution was, you know. Not only he demonstrated the existence of electromagnetic waves, not only he built an apparatus to show that electromagnetic waves exist, but in the process, he discovered something new called the photoelectric effect, something that he was not able to explain at his time. The photoelectric effect was only explained later on by Einstein himself, in 20, 30 years later. And the explanation of the photoelectric effect won Einstein the Nobel Prize in Physics. Okay, it was cited as being one of his crucial contributions for the Nobel Prize in Physics. But of course, he had even better contributions than the photoelectric effect. He formulated the theory of relativity, which, you know, was not understood by his peers at the time, so it was not cited by the Nobel Committee. And here you go. So everything, in a way, everything is connected, you know, with those late experiments of Hertz is connected with the 20th century physics. Here's the link between the classical physics and the modern physics, the physics of the 20th century that gave rise to relativity theory and even quantum mechanics. Okay, so that's how, what we're going to do here, we're going to prove using Maxwell's equations that Maxwell's equations leads to the equations of to the equation of an electromagnetic wave. It's possible to do that. We're going to work that step by step diligently. Many books has this explanation, but it's a very rough draw. It's just a draft of actually the derivation is supposed to be. So I'm going to do it in a more detailed fashion. Okay. So here we go. Here's the two little spheres, right? They behave just like a capacitor. And he did experiments on polarization of the electromagnetic wave, refraction as well. He was very thorough in his demonstration, his experiment. He didn't stop just at demonstrating the little sparks in there. He went even further than that. The photoelectric effect. See that? Hertz helped establish the photoelectric effect. That was later explained by Albert Einstein. Okay. So he is Hertz himself is a giant of physics, so much that we use his last name as one of the units of frequency. Okay, so let's close that, and I'm going to get here. I'm going to do the derivation of I want to demonstrate, I'm going to prove mathematically that the Maxwell's equations can lead to the wave equation. The wave equation that you're already familiar, right? Let's get my notes right here. Here's electromagnetic waves right here. And I'm going to get P39 notes. This one right here. So at this point in time, most of you have already taken physics 38, electricity and magnetism. Some of you haven't, right? Some of you have seen only mechanics. Today is June 23rd, 22. The electromagnetic waves. We start with Maxwell's equation. We start with Maxwell's equation. Something, remember what I usually tell my students, that if you have to memorize anything for the rest of your lives, are the laws of physics, and Maxwell's equations is a set of physics laws. We start. There are 4 integrals that you have to memorize. It's not difficult to memorize those integrals. 2 integrals are integrals over a closed area. Here you go. Closed area, here you go. And we must end this, closed area integral, right? And we must have a dot product between those 2 vectors. If you didn't memorize my physics 38 course, now is the time to memorize. It's not difficult to memorize at least the left side of the equation. Is a closed surface integral for both the electric field and the magnetic field. And then you have 2 other integrals that are contour integrals. There are path integrals over a closed path. Okay, so here you go. I'm gonna get a closed path integral right in here. Here you go, closed path integral. Both electric and magnetic fields, but that because it's a path integral is no longer dot dA, is gonna be dot ds. And we have another path integral. B dot ds. Okay. Now it's a matter of figuring out what goes on the right side, right? Here one is the easiest one. This one is the easiest one because there is no magnetic sources. The right side of this equation is going to be 0. It goes, since there is a source for electric field, and the source of electric field is an electric charge, what goes on the right side of this equation is the enclosed charge, the charge enclosed by the surface, by the closed surface. But we have also a constant. So we have almost half of those equations. Okay. This last equation here, we know that a source of magnetic field, right, is the current, and is going to be the current enclosed by the paths. And there is one more term due to Maxwell himself. Okay, I'm going to fill that up later on. In this meantime, let's worry about this one. This one is the law of electromagnetic induction. This one is Ampere's law, which, by the way, Maxwell discovered there was a missing term here. That was the key. The missing term was the key for the proof, the mathematical proof that electromagnetic waves existed, the theoretical proof that an electromagnetic wave existed. Experimental proof came later on. What goes here? What goes here is minus the flux minus the magnetic flux. And how do you spell out the magnetic flux? We spell out the magnetic flux as an integral as well. Equal B dot dA. Okay. But this is not a closed integral. It's like something like that. So what's missing here? What is missing here is the other term, similar to this one, by the way, okay? But instead of a magnetic field, we're going to have an electric field. Instead of a negative sign, we're going to have a positive sign. And to ensure that everything is in the proper dimension, we have to multiply by this constant, mu naught, epsilon naught. Those are the 4 equations of the electromagnetic field. When Maxwell discovered those terms here, the equations were not in this format. The equations were in a different format. Were just not even 4 equations, was far more than 4 equations. This format that you see here was not due to Maxwell himself, was due to someone else. Interesting history behind that. But it was due to Maxwell, this important term that nobody else saw at the time. The correction to Ampere's law. And now the laws of electricity and magnetism are finally complete. Okay, Maxwell didn't discover this law. Maxwell did not discover this law. He didn't discover this law either. And he didn't even discover this part here of the law. He discovered only this term here. And even though he contributes only the single term, we today call those four equations Maxwell's equations. And even the four equations were not formulated by Maxwell himself. He formulated those equations in a far more complicated fashion. You know, it was like 20 equations. Okay, that's the history behind the discovery. Okay, so we start with that. Let me put this one aside here. Okay, so the idea here, when we're looking for electromagnetic waves, we're looking at points in space that have no charges nor current distribution. Okay, and that's what we are going to solve those equations for. So here you go. The situation is something like that. You have a magnetic dipole, okay? A little loop in which you have a current flowing through this loop, and the current can flow. That's how you can look at this this problem. Let's see here. I want to put it on. It must be here. Line, yeah, this one right in here. Here you go. So let's say we have a current bouncing back and forth in this loop. Okay. But let's say at a given instant of time, the current is flowing in just this direction. Okay, I'm going to put here. That's how we start our problem. That's how we start proving the existence of electromagnetic waves. We start either with a magnetic, we call that a magnetic dipole. We start that either with a magnetic dipole or as an electric dipole. Either way works. Gives you the same final result. Start with a magnetic dipole antenna. Okay. So you can have an AC source here powering this dipole, this magnetic dipole. The first thing that you're going to say is that this magnetic dipole circuit is generating a magnetic field somewhere here in this region. There is no electric charges here in this region. There are no current distribution. The only current is restricted to this region right here. And if you have electric charges will be also restricted to the region, to the region of the source. And I want to know what's going to be the electric and magnetic field in this region of space where there is no charges and no current distributions. Okay, start as a magnetic dipole antenna. Here, you can also do that. You can also do that for an electric dipole. The result is going to be the same. I think the electromagnetic dipole is easier to illustrate. Okay, the idea is, find the electric and magnetic fields in the region far away from this current loop. Okay, so we want to find out what's going to be the electric and magnetic fields in the region somewhere around here. Just keep in mind that when I do those drawings are not in scale, okay? They are not in scale. In a way, they are an exaggeration of but sometimes we have to exaggerate for better visualization. Okay, so here you go. The first thing that we do is to figure out the direction of the magnetic field in that region that I mentioned, right? Here you go. Here's the region, right? I'm going to make a little bit larger. Hopefully, I'm going to encompass this region. Let's go right in here. I will copy. Let's make a little bit smaller. That's the region that we want to find out if there is any electric and magnetic field and which way they behave, right? Here you go. Here's the x-axis. I'm doing just the one-dimensional case, but it's possible to do the three-dimensional case as well. Although the three-dimensional case is for a more advanced course. Go. I want my illustrations to be perfect. Find electric in a region far away. I'm going to even put dashed here. Right, like that. Here you go. Dashed. Find the magnetic. Okay. So what to have here? We start. Generic magnetic field. Generic magnetic field in the region. Generic magnetic field due to the current distribution in the region of interest. In the region of interest. Okay. So here you go. We just do the right-hand rule, right? Get your right-hand rule, get the thumb pointing the direction of the current, and you discover that the magnetic field here in this region comes out of the page. That's the first step. Just notice that what we are doing is a mixture of qualitative and quantitative techniques, which, by the way, end up to be very powerful. What I didn't do, what's missing here? Okay, I gotta correct my equations, right? I told you that there are no electric current here, there are no electric charges here. So let's adjust my two equations to reflect that. Since in that region of the space there is no charges and no currents, the original Maxwell's equation becomes like that. Okay? No electric charge, no electric current. Now we have only electric and magnetic fields. Okay. This one doesn't take us very far, okay? This one is a 0 on the other side, so it doesn't take us very far. The first two equations doesn't tell us much. Do not tell us much because of the 0 on the right side. So we will concentrate on the last two equations. Okay, here we go. So I'm going to just go ahead, copy and paste those two equations here, right? And what am I doing? Now we know in that region, we have a magnetic field coming out of the page, okay? But there is more, Let's not forget that this current is changing as time goes by, right? This current here, is a function of time. I'm going to put like that because it's bouncing back and forth. Very important piece of information. Because the magnetic field is directly proportional to this current, right? My magnetic field will also be a function of time, right? Here you go. You want to write that down here? Magnetic field is also a function of time. And by the way, magnetic field is going to be a function of the position too, right? Did you notice? See, I put a larger circle here and smaller circle, just to denote to the fact that we're further and further away from the source. And because of that, the magnetic field is decreasing. That's why we have to put as a function of x and t. So I'm going to elaborate a little bit more on the previous slide. Here we go. In this slide here, I'm going to just state that the magnetic field is a function of position only, right? Because I still didn't tell you that this current is a function of time. Once I tell you that, step by step, once I tell you that this current is a function of time, then I'm ready to state that the magnetic field is also a function of time. Right? Here you go. Find the electromagnetic field in a region far away from this current loop. Okay, the genetic magnetic field with the current distribution in the region of interest. I'm going to do even better. I'm going to add on those slides. I'm not going to say anything about the, okay, then due to current, okay. Next one, magnetic field changes with position due to the distance, from the current distribution. The further away we are from the source, the weaker the magnetic field becomes. Okay, remember, I'm doing in details that you're not going to find. This detail that I'm doing here, you're not going to find in any book out there. Okay, I had to work that out. So in addition to that, let's current in order to generate an ENM field, an ENM wave, current must change with time. Okay. So here again, I'm not going to put time dependency yet. Okay. Since current changes with time, since current changes with time, B field also change with time. You're going to have a variation in space and time of the magnetic field. Okay, now I don't need that anymore, right? Don't need this slide anymore. Let's play this, let's play this movie again. Just treat that as though it is a movie, right? Start with a magnetic dipole antenna. It's a current loop. Current loop with a current that changes in time. So let's say at a given instant of time, the current is flowing in this direction. And then you can repeat the same procedure, the entire procedure for current in the other direction. You're going to get the same result. Okay? We are going to calculate the behavior of the magnetic field here in this spot, and maybe the electric field as well. At least we are going to have a magnetic field here in this region because of this current distribution, right? And we do have a magnetic field, which, by the way, changes with position. The further away you are from the source, the weaker the magnetic field is going to be. And that's what this illustration is telling us. B is a function of position X. This is a one-dimensional case. Okay, like I said, I'm exaggerating here. These drawings are not in scale. Well, I'm exaggerating just to make it easier to understand what's happening there. In reality, this region is much smaller, right, in the vertical direction. This distance is much further away as well. One more. Okay, now I introduce the fact that the current changes with time. Okay. Since the current changes with time, the magnetic field must also change with time. And now something interesting happens. When the magnetic field changes with time, we go back to our Maxwell's equation, and we recall, right, from the law of electromagnetic induction, that changing magnetic field, or also in a more generic sense, a changing magnetic flux induces an electric field. Remember that? Okay. So going back here, that's the type of magnetic field that's the type of electric field that we get. So let's say at a given point in time, my current VIDT is positive, right? At a given point in time, my DIDT is positive. Take DIDT to be positive at a given instant in time, right? If DIDT is positive, don't forget that B is proportional to I. It also means that dBdt is also positive. dBdt is also positive. Okay. This implies that dBdt is also positive. And now, why do we need this piece of information? We need this piece of information to find out what's the direction of the induced electric fields. Okay, so here you go. So induced electric field, induced E field circulates around B, right? And that's what we have here in this next drawing. Let me get that. I'm gonna copy everything here since I already have, you know, and here you go. But because magnetic field is increasing, the electric field must circulate in the direction opposite to the magnetic field. Okay? Circulate around B in the opposite direction. Several steps to show the electromagnetic wave, but those are it is difficult because it involves several steps, right? It's not just one or two or three. Look at how many slides I already have. Okay, what comes next? Okay, let's see, I don't need that anymore. Changing magnetic field, here you go. Let me put that here. Changing magnetic field. I don't need that anymore, right? Changing magnetic field induces electric field, an electric field in the clockwise direction. I don't need this other one anymore. What comes next is important as well. Okay, so here you go. I'm going to simplify my drawing by removing this box. I don't need this box anymore. Okay, this box was necessary only at the beginning. Oh, and by the way, E fields. Notice what's happening here. You know, here, this electric field that you have at the bottom of this magnetic field, right? Points in the direction opposite to this other electric field. You see that? Similarly, we have here, and you have for the other ones as well. Okay, so E fields between B fields cancel out because they point in opposite direction. So I'm going to use another box like that to emphasize the fact that, you go, this field here cancels out, this electric field cancels out. You go. Okay, you go. You go. Maybe I should put it in a different color so it stands out from everything else, otherwise it becomes invisible, right? I'm gonna put it a red color. Nope, not this one, it's this one here. Here you go. E fields between B fields cancel out because they point in opposite directions. Okay. But not only, oh, by the way, not only we have those B fields canceling out, but then we also have, okay, so don't forget that we still have if fields here, right? Let me go to the next one, next slide too. I'm not putting enough. Group. Group, you go. We still have electric fields pointing up here, right? You go. Same here. You go. Same here. And let's not forget that we also have electric fields circulating here on this side, right? So like that. I'm gonna put it right in here. Another one here. Another one here. Right, here you go. Okay. So when we analyze this situation, what's left out? Okay, what's left out is something like that. Here you go. We have an electric field. Electric fields only in this vertical direction here, right? No electric field in the horizontal direction. Make sense, right? So now I can remove, let's see, yep, can remove that to simplify my drawing. The less elements in the drawing, the easier to understand it, right? All these other drawings were used to create what I am displaying right now. Oh, go. Electric field. There will be a, let's see, I didn't call it. Let me see what's going on here. Yeah, I missed this one here. Here you go. Yeah, I missed this one here. Okay, let's copy that again. Let's see. Cancel, 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 cancel. Simplifying the drawing. Here you go. This one gone, this one gone, this one gone, this one gone, this one gone. This one. Okay. Remove all those arrows of the electric field, because now we can display the electric field in an easier fashion. Did I remove something I didn't want? Here you go. Yep. All those horizontal electric fields cancel out because we have more magnetic field lines there at the top. Oh, no, I don't want that. Good. go. Right? Next to this magnetic field, the electric field points downwards. Next to the left of this magnetic field, the electric field points upward because the electric fields are circulating this direction, right? Oh, the electric fields are circulating in the clockwise direction. So we must have also a cancellation of the fields because this one is pointing upwards and this one is pointing downwards. But there is an important detail. Let me draw this electric field in a better way. Here we go. I'm gonna put it, yeah, here we go. I'm gonna make this electric field line shorter for a very good reason. Why is that? There's a very good reason why this electric field line is shorter. Anybody can tell me why, if you're following? And I'm going to change the direction of this one as well. Uh-oh. Yeah, here you go. And then we have something similar here for the next pair of electric field lines. It should be shorter than the other as well. Why is that? Anybody can volunteer a reason for that? Well, the reason is simple, right? If the magnetic field here are weaker than here, consequently should be the electric field lines generated by it, right? That's the reason. If fields between if fields in the horizontal direction, if fields in the horizontal direction cancel out. That's a better way. Okay. If fields in the horizontal direction, we can have the same title here. If fields in the horizontal direction cancel out. Okay. If fields in the horizontal direction cancel out and decrease the distance, just like the magnetic field. What those electric fields are? Those electric fields are induced electric fields. Okay. So we're getting there. So I don't need that anymore. We're coming to the point. Okay. And then what's next? Okay. Part of this field is going to cancel out with part of this field, right? So the net field, the net electric field is going to point downwards, right? I'm going to make a little bit smaller just to emphasize the fact that some of these fields got canceled out. Here we go. If fields cancel out. Okay. If fields point downwards. So before we go into a break, let's make a brief summary, right? And then we continue after. Remember, this is a lengthy derivation. That's and you're not going to see anything like that out there. So you start with a magnetic dipole antenna. This magnetic dipole antenna, we know this is going to produce a magnetic field far away there in space. Okay, here you go. At least, right? Why does the thing keep on showing up? Let's see. Yeah, good. Now it doesn't show up anymore. It's going to produce a magnetic field in that region very far away. And because we have no electric charges and no electric currents, Maxwell's equations becomes simplified, right? Without charges, without electric currents. Here are the magnetic fields. The magnetic field decreases as you go further and further away from my source. Okay, the decreasing magnetic field is depicted by the size of the circle. The direction of the magnetic field is depicted by this point here. Magnetic field changes with position, right? But don't forget that the current changes in time as well, because the current changes in time. Is an electric dipole antenna that's connected to a AC generator. The magnetic field, because the electric current changes in time, the magnetic field is also going to change as time goes by. Now we introduce the fact that the electric current, the rate of change of the electric current is positive. The IDT is positive. We need this information to know how the magnetic field behaves, because the IDT, if you could have repeated this whole thing for negative here as well, and you would get the same result. If the IDT is positive, it means that the BDT is also positive. Why do we need this information? Because if the current is changing, if the magnetic field is changing, okay, the current is changing, magnetic field is changing. Now I need to know how the magnetic field changes, because a changing magnetic field induces an electric field. If we know how the magnetic field changes, we will know how what's going to be the direction of the induced electric field. That's what we're doing here. Here you go. Electric fields induced around the magnetic field lines. In this case, it's going to be in the clockwise direction, because the rate of increase of magnetic field is positive. But then we recognize that those electric fields here at the bottom, they cancel out. Because they are all at the same distance from the source, the magnitude of this field is going to be the same as the magnitude of this electric field. Consequently, it's going to completely cancel out. Right? Here you go. Here's the electric field circulating, right? But only the horizontal electric field is canceling out, not necessarily the vertical ones, which leads to this drawing here. I must put another electric field line here. Oh, you know what? Yeah. Another electric field line here. This electric field line has the same intensity as this electric field line. And these electric field line has the same intensity as this and same intensity as this, right? In the next step, we superimpose those two fields. But this electric field must be stronger than this one, because it's closer to the source. It's also being induced by a stronger magnetic field, right? So in the next step, we get something like that. And so let's put another electric field line. Let's see. Yeah, this electric field line should be downwards, right? Because we have another magnetic field line here that I didn't draw. So it should be a little bit intense, okay, stronger. 908. Okay. I'm going to do something else too. Here you go. I'm going to write down my induced electric field, and I'm going to put that in red color. So you know that those lines mean induced electric field. Here you go. Induced electric field, right? So let's go for our break, right? Any questions about that? Let's see if there are any questions here in the chat box. We have 31 issues. Before we go for the break, let me take attendance. And then we continue. It's gonna, like I said, it's gonna be. So books usually they do something very quick that lacks lots of details and important steps. P39 attendance roster. Here you go. Lecture. Today is the 23rd. Toby, are you there, Toby?
Yeah, I'm here.
Good. Harun Atif. I saw Harun coming. Are you there, Harun? Harun is here, but it looks like he's away from his computer.
Yeah, I'm here, Professor.
Okay, good. Thank you. Musa, are you there, Musa? I see Musa as well, but he's not answering.
Yes.
Okay, good. Thank you. Zachary Blue.
I'm here.
Are you there, Zachary? I hardly could hear you.
Yes.
Okay, good. Thank you. Elena. Good. Luis Crystal. Are you there, Crystal? I don't see Crystal. Okay, so Brian Spino. Are you there, Brian? I don't see Brian. Robert Faust. Hi, Robert. I know you're there. Yeah, I didn't get to you yet, Pedro. Hang in there. Okay, Pedro is here. Lawrence Flores.
I'm here, Prof.
Okay, Daniel Freire.
Here.
Okay, Mamalia Gale.
I'm here, Professor.
Thank you. Tiffany Wang. Olivia Kruger.
I'm here.
Next is Daniel Liang. Good. Sarina Lubana. Sarina there. I see Sarina listed here, but I don't hear her. Let me put a star. Anthony Lopez. Good. Next is Chuck Lu. I don't see Chuck Lu here in the list. Okay, next is going to be Dave Maes. Good, thank you, Dave. Ryan McNeil. Hi, Ryan. Alexis Nigret.
Here.
Thank you. Daniel Nwagbo.
Yeah.
Okay, David Nwagbo.
Here.
Good. Next is Claire Ottinger. I see Claire in the list. Hi, Claire. Okay, I'm gonna put a star here.
Here. Sorry.
Okay, good. Thank you. One more student coming. Must be Dave. Yeah, okay. Jennifer Ramirez. Next is Noah Raymond.
Here, Professor.
You're there, okay. Next is George Risp. Don't see George. Shah Safi.
Here.
Okay, next is Natalie Santiago.
Here.
Next is Nathan Silva. Nathan is not answering, but he's listed here. I'll put a star. Next is Danis. Okay, thank you. Kenny Villagomez.
Yeah, I'm here, Professor.
Okay, Nolan Williams.
Yeah, I'm here.
Good, and Mengshu. Okay, now what about Olivia? Olivia, are you there? I don't see Olivia. Okay, and we have a total here of 28. We have 31, 30, 29. 2 students that has a star. Yeah. Sarina, are you there? Sarina and Nathan. I don't hear from them. Okay, so let's have our break. It is 9:15. Let's go until 9:30. Break till 9:30. See you then. Right? Okay, here you go. Recording in progress. Good. So here you go. That was our last slide. Okay. Oh, that was our last slide. And what we have to do next, I'm going to identify the electric fields. You know, this electric field, not BC. I'm going to call it electric field at position X, instant of time T. And this other one, I'm going to call the electric field at position X plus delta X at the same instant of time T. We're going to use that in one of the equations. Okay, and how we're going to use it? We're going to start using our integral equations. As of now, we have been using just a qualitative treatment to find out how the electric and magnetic field behaves in that specific region of space. Okay, we still didn't use our Maxwell's equation. And now we are going to use one of them. We're going to use one of our Maxwell's equations. We are going to come up with a loop in the region of the magnetic field, right? So here we go. Let's see, we got a, yeah. What's going on here? Here we go. So here you go. What we're going to do, we are going to come up with a loop, an Euclidean loop right here. And let me do a better job here. I'm going to copy and paste here. And now I'm going also to simplify my drawing to keep as little information as possible, only the information that's really required, okay? I'm going to eliminate my magnetic field lines to help you out with the proper understanding of the problem that you're doing. Okay, I don't need this information anymore. I'm going to move this guy here down so it's not too much. Okay, and I'm going to come up with the loop. With a loop of this integral here. Do you see here? We have a line integral over a closed path. Okay, and I'm going to come up with a loop that can be applied to that drawing. Okay, first the loop, and then we label everything. Lawrence is coming. Here you go. Here you go. Right, here you go. Here's a loop. And I want this loop to be transparent so we can see what is going on there. No fill. I'm gonna, I'm gonna shrink it a little bit too, so it's not overlapping with my electric field. Like that. I'm not gonna choose the path, the direction of the path yet. right? Remember, a little bit off so that we manage to see the fields, right? There's a reason why I choose this loop. The equation, I'm going to copy this equation and paste in there. Okay. And go even further. Let's see, you go first the equation, then the loop, right? First the equation, then the loop. You go switch it here. Fields, simplifying the drawing just to show the electric fields. Okay, and now just that, not just the electric field, but also the one of the Maxwell equations. Okay, first the simplification, then the simplification is the Maxwell equations, the simplification, the Maxwell equation, and the loop. This loop that you see here is going to be applied to this integral on the left side of the Maxwell's equations. By doing that, we will be able to show that the Maxwell's equations reduces to the wave equation. There's more to come. Bear with me. Next. Right, and I'm going to label also. Oh, not just label. First, let's get the direction of the loop. And then we label the arms of the loop as well. I decided to take this direction of the loop. Why is that? There's a reason why I choose this loop direction, because it rotates in the direction of the magnetic field. Okay, I chose this direction. You could have gone the other direction as well. You'd have gotten the same result that you're going to get at the end. Okay, and what we have to do next, we have to label the arms of the loop. Okay, we're going to solve this equation here, this left side of the equation now. That's why I'm doing this loop. Arm 1, arm 2, arm 3, and arm 4. What else am I going to do? I'm going to come up with a generic, here you go, arm 1, 2, 3, and 4. And I am also going to come up with a length for this side of the loop. Okay, I don't need to, well, this length you already know is delta x, right? This length here you already know this delta x. But I'm going to come up with this arbitrary length L for this side of the loop. I'm going to eliminate this electric field too because it's in the way. Okay, here you go. And I'm going to emphasize that this length that you see here is delta x. Okay, a rectangle of length L and with delta x. Let's come up with a better. I don't like this color that the PowerPoint uses. You know, it's a faint blue. I prefer the black. For some reason, they have chosen that faint blue color. There you go. Position X, position delta X. Can I do a better? I want to make it thicker. Thicker than that, yes. Here you go. And we have to do this other one as well. Here you go. Right here. So we have everything that we need to solve the left side of the integral right now. I don't need that anymore. Okay. So here you go. Let's do that together. This integral can be broken down into 4 integrals. Integral over the past number 1, integral over the past number 2, integral over the past number 3, integral over the past number 4. Okay, so here we go. Going back to my notes, this one here. We're dealing with this one right now. Working the left hand side of the above equation while referring to the illustration. Right? Here you go. Okay, here you go. That's E dot, I'm going to put like that. E dot ds. Right? Over past number 1, E dot ds over past number 2, E dot ds over past number 3, E dot ds over past number 4. It doesn't have it. Huh? Interesting. We used to have something here. I saw it doesn't have everything, huh? It's strange. Ah, what a shame. I can't find. Okay, so how am I gonna do it? I'm gonna put it, okay, I'm gonna put it this way. I'm gonna use this notation here. It's not the ideal notation, but I'm gonna use this one here. Past number 1. Okay. Past number 2. Past number 3. Past number 4. Ideally, those numbers should be next to the integral, but I cannot find the proper sign for that. Okay. Okay, let's go to past number 1. Past number 1, the direction of integration is the same direction of the electric field. That's going to be the electric field in the x direction, in the x at the x position, right? And because they're the same direction, E dot ds is going to be E ds. Make sense? So here you go. This first integral is going to become E xt ds. Okay, along the path number 2, here you go, we don't have any electric field. The electric field is perpendicular to the direction of the path number 2. See that? 90-degree angle. So integral over path number 2 becomes 0. E is perpendicular to ds. E dot ds over path number 3 is going to be negative because the path runs upwards and the electric field runs downwards, right? So here you go, I'm going to put a negative sign here, and they're anti-parallel to each other. And what else do I have to put here? I have to put a delta x. A delta x inside the parentheses. And finally, we also have over path number 4 is going to be 0 as well, because the electric field is perpendicular to the direction of the path. Okay. What else can we do? There's one more thing we can do here. Okay. The electric field depends on the distance x alone, right? The electric field changes along the direction, but at this specific position, the electric field doesn't change at all. Even though this electric field is greater than this electric field, the electric field at this point is the same as the electric field at this point, which is the same electric field at this point. Because of that, we can take out this electric field from inside the integrand. We do not need, by the way, the pass over 1 anymore. The ds is going to be L. We have the same thing for this one here. Here you go. And we do not need to specify the pass either. Okay? We can eliminate the 0. We can eliminate the 0. And now the ds, the integral of the path ds becomes L, the L that we do not know. Let's see if we can, if you're going to have the L or not at the end. Okay. So that's the left side of this integral here. Now we are going to worry about the right side of the integral. So here you go. Let me write it down. I'm going to copy and paste here. We don't have L here like that, right? And now we have to worry about this integral here, right here. Okay, don't forget, this is a flux, a magnetic flux over an area. And by the way, the area that we are talking about is the area enclosed by the loop. Okay, is this area here. Don't forget that we have a magnetic field there inside, right? I'm going to fill up the magnetic fields there. And now we do not need the electric fields anymore because we already used them. I don't need to label the paths anymore because we already worked out the integral, the path integral. I don't need simplifying as much as we can. We're going to worry about the integral, the right side integral. So let's document here. We calculate, you know, the next one here is going to be calculate the left side of the integral. calculate this, the integral, calculate this integral. Okay. Here you go. Choose the right path to calculate the left integral. Okay, go. Now get the right direction of the path integral. In this case, counterclockwise. Get not the right direction, get any direction of the path integral. In this case, we chose counterclockwise. Number the path. Number each branch of the path integral. Right? Pass 1, pass 2, pass 3. What else do we need? Now we're going to calculate the right side of the equation. Calculate the right side of the equation. That's what you're going to worry about now. No, wait a minute. No. No, it's not the right side. Finish the left side, right? Finish the left side of the integral. What's going to come next? Now we are going to calculate the right side of the integral. Calculate the right side of the integral. All right, here you go. Number each path, get in the actual. Choose the right path, not the right path. Choose any path to calculate the left integral. Calculate the left integral. Okay, that's Faraday's law of induction. Faraday's law of induction. All right. So now what else do I have to do? I have to fill up this area, right, with the magnetic field that I had abandoned before, remember? So let's go back there. I abandoned them before because I want to simplify the drawing. So, but now we need those guys back. Let's put that back in there. Here you go. Magnetic fields. Yeah. Here you go. Like that. Delta X. Now we can calculate the flux. Okay. Let's not forget, I gotta put back that direction of the pass that we choose here. I gotta put the pass here back. Yeah, okay. So we are rotating the direction of the magnetic field. Okay. Let's do that. So here you go. This is a small delta X. Because the delta X is very small, we can say that the magnetic field is roughly uniform throughout this region. Okay, so here you go. Let's go back here. Now, Okay, magnetic field here. Oh, by the way, first we recognize that B dot dA is going to be BdA because the area points in the magnetic field points in the same direction of the area, right? We are rotating in the counterclockwise direction. The thumb that represents the area vector points in a direction parallel to the magnetic field. So that's the first step. We take the dot product, we get BdA. In the next step, we recognize that the B is a function not just of the position, but also a function of time. Okay. And what else? We are integrating over X, right? We are integrating over X. So here you go. Because the delta X is very small, because this delta X here is very small, we can state the magnetic field within a small area is going to be almost constant. If the magnetic field over this area is almost constant, we can take the B field from inside the integrand. Okay. Since you are integrating over the area, we lose our X dependence. Let's see. No, we don't lose the X dependence. We keep it. Yeah, we keep it. And now we have to worry about the area, right? We have to worry about that area. I'm gonna this area. Let's take a look at the area. The area is gonna be what? L delta X. By the way, this cannot be a total integral because the B is a function of X and T. It has to be a partial derivative. It cannot be a total derivative. It has to be a partial derivative. Here you go. Partial derivative here. Partial derivative here. Okay. And that's the equation you are getting, and that's what that one of those integral equations lead us to. We're not done yet. We're not done yet because we have used only this integral here, only this integral equation. Now we have to use this other integral equation, and the procedure is very similar. The procedure is very similar, but now we have to do in terms of the B field. Okay, so let's do that. What am I doing here? Let's see here. Okay, I have to. Yeah, this electric field cannot be here, right? The electric field cannot be here. Now in the next one. We don't need that anymore. Okay. Oh yeah, there's one more step that we can take here that I didn't tell you. Yeah, there's one more step. Yeah. Okay, there's one more step that we can take here. Here you go. This L cancels out with this L. Okay. And then what else? This delta X can go to the other side, right? And now you recognize what the left side is. We take the limit as delta X goes to 0. And what do we get? This equation here on the left side becomes another partial derivative. Partial derivative with respect to X. Here you go. that our first partial derivative equation. Okay. And then we repeat the same procedure for the remaining Maxwell equation. Maxwell's equation. I'm not going to do that because it's going to take too long, right? This thing has taken us already 2 hours to do. So it might take another 2 hours to do this one as well, but the procedure is very similar. Okay, here you go. Repeating for this one here, what do we get? Okay, remember it was the E that was in the past integral, right? I'm gonna put it side by side. Okay, this integral results in this partial derivative, right? And look, those integrals are similar, right? All you gotta do is to change the E to B, right? So here you go. And the B to E. Here you go. Here we change from E to B. Here we change from B to E, right? But then there is a little dx. Then there you have this constant here. Oops. We have this little constant that the other one doesn't have. Okay. And you still get the negative sign, by the way. Okay? And now we have those two equations, those two differential equations, partial derivatives. Is this the wave equation? Not yet, right? Maxwell's equations result in the above two partial derivatives. Okay. The question is, are these the wave equations? Well, they don't look like the wave equation, right? They don't look like the wave equation, but we can get those two equations to become the wave equation. Do you remember the wave equation? How was the wave equation? The wave equation is supposed to look like something like that. Here you go. Partial derivative, second partial derivative, right? Second partial derivative. And you gotta put a second here. And then we have to fill in with the proper parameter, right? Is that the right one? Let me see if that's the right one. You gotta do here is meter divided by second square, right? Meter divided by second square. Yeah, okay, here is meter divided by meter square. So 1 divided by meter, meter divided by second square. Okay, here is meter square per second square. Yeah, that's the right. But it doesn't look like anything like that, right? Those two equations. But we can get those two equations to look like this one. How do we do that? It's a rather straightforward way. All you have to do is to differentiate this with respect to x. Okay? To make our two partial derivatives look like the wave equation, we differentiate the left side of the second equation with respect to x. With respect to x. Or, you go. We get that. I'm gonna remove this one here. You go. I'm gonna put that between parentheses. we apply this operator, right? ddx. Now we're going to start to look like, we're going to start to see it becoming something like the wave equation. Okay. What else do we have to do here? I'm using only this equation. Now I need to use, I already used this equation. Now I have to use this one. How can we use the first one? Oh, you can commute the partial derivatives here, okay? So commuting the partial derivatives, we get something like that. And now we substitute this equation in the other one, okay? So here you go. I'm going to copy and paste it right in here. Look how nice it gets. That's what Maxwell saw at that time, okay? We're getting a second derivative in time, right? For the electric field. And mu naught epsilon naught can go outside. Second derivative in time. Second derivative in time. Here you go. And now the question is whether those two parameters has units of velocity square, inverse of velocity. Yeah, it does have units of velocity square, okay? And if you calculate this guy here, you're going to get the following. At that time, you know, Maxwell knew values of epsilon naught and mu naught, okay? I'm going to copy. And when you calculate that, you do get the speed of light. You can, actually it's the inverse of the square of the speed of light, which ends up being exactly the wave equation, okay? That's what Maxwell did at the time. Just something like that, not exactly like that, but just somewhat like that. That physicists were suspecting that the electric and magnetic field behaves like a wave, but nobody had proven it. And that was the proof, the mathematical proof that the electric and magnetic field behave like a wave. Repeating, here you go, for the magnetic field, right? You can repeat for the magnetic. I did here the partial derivative with respect to the partial derivative of E, right? But what if you repeat for this one instead? You do ddx here, right? You get ddx on the side as well, commute the dt with the dx, and then substitute right here. You all repeating, here you go. Repeating for the other equation, for the other partial derivative equation, you get the same thing for the magnetic field. Go. Now you have both the electric and magnetic field behaving like obeying the wave equation. Okay. Not only the E and B fields obey the wave equation, comma, but they are also perpendicular each other. Okay, so here you go, from here, right? It turned out to be perpendicular from this whole drawing that you see here. Right, here you go, the previous one. Oh, right here. But this is true, but wait a minute, but a word of caution, P and B are perpendicular only in the vacuum. For other types of medium, for other types of media, they may not necessarily be perpendicular. Like in the case of an optical fiber, for instance, an electric and magnetic field propagate inside an optical fiber. Light, right, propagate inside an optical fiber, which is a electromagnetic field. The electric and magnetic field, they are not necessarily perpendicular to each other. They may be, within a certain approximation, but in general, it's not. To let you know, I am here, but I have been having. Okay, thank you, Sarina. Let me get. What about George? Are you there, George? Sarina, or is Sarina right in here? Let me see if George is here. Yeah, George is not here. He's not listed anymore. Okay. We have 29. Yes. Okay. Okay, so here you go. So that's what we have. Well, one more thing. Okay, now let's see. It's 10:15, right? Let's go another 15 minutes. Yeah, let's go another 15 minutes because there's time to do other things. Okay. Both the electric and magnetic fields satisfy the wave equation. And what does it mean? Let me copy that. I'm going to repeat that here. Go. A wave, and by the way, a wave that propagates at a speed c equal to 300,000 kilometers per second, okay? Which is the inverse of a square root of epsilon naught mu naught. Don't forget, right? See that? This guy here is equal to this guy here. And when you do the mass for the inverse of mu naught, epsilon naught, and the square root, you get 300,000 kilometers per second. Just get that from any book, do the math yourself, okay? You're gonna find that out. Okay. So you are ready. Okay, so what is the next question is, what is a possible solution? What are possible solutions? What are possible solutions to the electric and magnetic fields? And magnetic fields. You have already steady waves, right? And you already know that a possible solution to the wave equation should be something of this nature, x minus vt, right? That's one possible solution. And you should expect the same for the magnetic field. Maybe it's going to be a slightly different function of B, but it's still going to be x minus vt or x plus and minus vt. Let's make more generic yet. X minus and plus vt. Minus is the forward propagated, plus is the backward propagated, right? It all depends on the position of the source, right? If the source is right in here, the electric field is propagated, the electric and magnetic field are propagated from the left to the right. From the left to the right, that would be the forward propagating. But on the left side, you'd have the backward propagating electric and magnetic fields, right? Minus, right? X minus vt from the left to the right, x plus vt from the right to the left. Okay, so that would be the most generic What is the most genetic solution of the electromagnetic field? Okay, that's the most genetic solution. So the next question is, what is a more specific solution for the wave equation of the electric and magnetic fields? Okay. A more specific solution is that one that I told you before, right? The one that's very important, the plane wave. Okay, the plane wave, that's a possible solution. Is the most useful that we're going to find out. Not only is the most useful, but also the simplest one that we're going to find out. Okay? So we can here write our electric and magnetic field in terms of a planar wave. In terms of a planar wave. And we're going to do that right now. And from there, we are going to find other things. We're going to discover other things about the electric and magnetic fields. Okay, so what are we doing? This whole thing that I did like in 3 hours, right? 2 hours and a half. The book did in only 2-3 pages. Okay. But that's because he skipped lots of important things that we end up finding out on our own. Many books out there don't go through the trouble of do the step-by-step derivation that I did. Okay, so here we go. Wave equation. Yeah, here you go. I'm going to do according to the book. Okay. The plane wave. So this is a specific solution for the plane wave. Look like that. Here you go. A magnitude, right? Sine is a plane wave. Sine of what? K. That's the way I like to do, right? X minus VT, forward propagating. Okay. The magnetic field will have a similar solution, but the amplitude is going to be different. Okay. This is the amplitude. This V you already know is a C, right? Velocity of the light, 300,000 kilometers per second. Okay. And what else can we do? Okay. We can find out. Okay, K depends on the wavelengths, and that's going to be dependent on the wavelengths of the electromagnetic wave we're talking about. The wavelengths of the electromagnetic wave we're talking about is going to depend on the frequency of oscillation of your circuit. Okay? Circuit. Right? We can get it to oscillate at 60 hertz, for instance. We can get it to oscillate at 160 hertz. No, you can get it to oscillate at the frequency of your favorite radio station, right? 98.2 megahertz, right? And so on. Depending on the frequency, you're going to get a given wavelengths. The speed is not going to change. It's going to change only if it propagates in different media. In vacuum and air, it's still 300,000 kilometers per second. But then if you choose a different media, then like I said, the electric and magnetic fields are no longer going to be perpendicular to one another. It's going to be almost perpendicular, but not completely perpendicular. Okay, in our illustration that I did here, okay, here you go. The electric field is along the y direction. right? In the negative y direction, the electric field. And magnetic field is along the positive z direction. Do you see that? X in this direction, y should be upwards, right? And z should be out of the board. B along the z direction, electric field along the negative y direction in this specific case. Okay, so what can we do now? Okay, so we would know what K would be. We already know what C is. And K again is going to depend on the frequency of your circuit. X and T are independent variables. What we do not know is the magnitude, is the amplitude of the electric and magnetic fields. We do not know that. The next thing we can do, okay, let me go. The parameter K inside the solution, inside the wave, inside the planar wave, depends on the frequency of the magnetic dipole that I mentioned before. Okay. The velocity of the wave is known to be c, and x and t are independent variables. The only thing, those we know, those we know what their values are. What we need to find out now, are the amplitudes of these two waves. Okay. EM and E sub B and B sub M. E sub M and B sub M. We cannot find the specific, we cannot find their specific values. However, we can find how E sub M and B sub M relate to each other, to one another. Okay. How do we do that? We're going to do that right now. What did I do? One another. Here you go. We find that out. We find that out by using the initial partial derivative. By using the initial partial derivative. Okay, and the partial derivatives I'm talking about is those ones here. Here you go. Let's go get it. This one. See, we got this partial derivative. We got this other partial derivative. Let's see, that's one partial derivative. And what's the other partial derivative? Oh yeah, we have this other partial derivative here. Okay. So here we go. Let's use this one. Okay, so here you go. Here. Right, dE dx. What's dE dx? dE dx is dE dx is going to be E sub m. Here you go, E sub m K, right? Cosine of Kx minus Ct. Okay. And then we do for this one as well. Okay, dB dt is going to be what? Is going to be cosine K minus Kc, right? Minus Kc. Have you ever heard of Kc sunshine, man? You go. You go. Minus cancel with minus. Right? You go. And then cosine is going to cancel out this cosine. K cosine is going to cancel out this K cosine. Right? That's going to be the next step here. Okay, K cosine is going to cancel out this K cosine, and we finally have a relation between Bm and En. Em. We do not know what Em is. The Em we know we can find Em only from the power of the radio station. Okay, that's what defines. But at least we know that the magnitude of the magnetic field is tied up with the magnitude of the electric field. Okay. So that's a very important. We can repeat for the other one. Let's repeat for the other one. For the other partial derivative equation. Here go this one here. Let's see if we get it. Huh? Okay, here go. Repeating for the other partial repeating for the other partial derivative equation. We get B. I'm going to put it here inside, and then I can, right? And then we do the E. So they're supposed to result in the same equations, right? If it doesn't, there must be something wrong with the equations. Okay, so here go. This one, Bm goes out. I'm doing a slightly different way that I did before, right? Cosine becomes cosine. We are differentiating with respect to x, so it becomes K cosine. Okay. Okay, so what about this one here? Is going to become cosine as well, right? And it's going to be minus Kc, right? Are we going to get the same thing? Let's see here if we get the same thing or not. Huh? Negative cancel out with negative. K cancel out with K. Cosine cancel out with cosine. Let's not forget that C is 1. C is, okay, let's go get it. C is the inverse of the square of mu naught, epsilon naught. Right? No, it's not what I want. It went like that. Here you go. Let's see if we get it or not. And this one cancels, become, okay. Remember that what you have here is c squared, right? Do you still get the same result? Is that c squared? Let me see. Oh no, it looks like I made a mistake here. Let's see. I made a mistake somewhere here. Negative is negative. K cancel K. Cosine cancel as well. We have this, right? Okay, here you go. We're gonna do differently. Yeah, I made a mistake there in the conversion of mu naught epsilon naught. Here you go. This guy here is 1 divided by c squared. Okay, was mixing that up, right? And now c squared cancel with c. And E gamma becomes something like that. And we get exactly what we got before. Okay, here you go. Using 2 different equations from 2 different Maxwell's equations, we get the same result. Okay, okay, so here you go. What are the solutions to the wave equation? Now we can here write that in terms of the same amplitude, right? Here you go, like that. And that's the relationship for the wave equations, the electromagnetic wave equations. Just remember, E and B again, I'm going to repeat here, E and B are perpendicular to each other. Okay. How do you represent it here? Let me see if I have a nice representation of an electromagnetic wave here. If I don't, we have to look else. No, I don't have a nice representation here. Maybe Wikipedia has. Let's take a look at their Wikipedia. No. Let's take a look at representations of electromagnetic wave. Electromagnetic waves. Electromagnetic wave. Okay, here you go. That's a representation of the electromagnetic wave. See that? The planar wave, it behaves just like that, right? You have seen that before, right? Just imagine your wave propagating a string, but now it's no longer a string. The string is the medium, right? Your mechanical wave is a medium, but now we do not have a mechanical wave. We have an electromagnetic wave. We have vacuum. We don't have any medium whatsoever. We have vacuum. But the electric fields moves up and down just like the points in your string. And the motion of the electric fields, vectors, they trace this wave pattern in the invisible space of the vacuum. That would be the electric field. Okay? The magnetic field would do the same. Remember, magnetic field is perpendicular, right? To the electric field. So it would oscillate, in this case, it will oscillate along the y direction, back and forth at an angle that's 90 degrees. Let me see if I have a simulation here. Oh, here you go. Here you go. That's let me see if I cannot do better than that. Okay, electric and magnetic field. So it gives you the impression that the thing is moving from the left to the right. Well, actually, it does move. The energy moves from the left to the right, and the magnetic field tags along with the electric field. Here is the wavelength. See the wavelengths? The wavelength of the electromagnetic wave. The wavelength of the electromagnetic wave is going to depend. Here you go. The wavelength is the distance from here to here, right? Peak to peak. The wavelength of the magnetic field is also the same as the wavelength of the electric field. The wavelength of the electric and magnetic field is going to depend on the frequency of oscillation of your circuit. Okay. So if it's 60 hertz, if it's 120 hertz, and so on. But in the case of electromagnetic waves, it's not just 60 hertz, it's not just 120 hertz, it's far more than that, especially when it comes to light. The frequency is very high. Let's see if we have the frequencies here. Okay, here you go. Here are the frequencies and wavelengths of an electromagnetic wave, okay? The higher the frequency, the more energetic the electromagnetic wave is. So here is gamma rays, okay? Those gamma rays and X-rays and part of the UV waves are considered ionizing radiation. Radiation that ionize matter, can strip out electrons from atoms and matter in general. That's why it's no way it's dangerous. Okay. Visible spectrum is right here, a very small slice. And look at the frequencies. 10 to the 24 for gamma rays, right? Long radio waves around 1 hertz. Here is 100 hertz. 100 hertz should be what you get from our power line here, right? If you go to your microwave oven, it's 10 billion hertz, right? 10 to the 9 times 10. 10 to the third is 1,000. 10 to the 6 is 1,000,000. 10 to the 9 is 1 billion. So it's 1 billion, 10 billion hertz. And here's the respective wavelengths. Wavelengths vary from 10 to the 8 to 10 to minus 16. Okay. That's what we have. Let's see if we have anything else. Well, it's time for our break, right? It's already 10:41. Any questions about that before we go in our break? Okay, and going back to my notes here. Okay, so let's see, it's 10:40. Let's go to 10:55. Break into 10. Break till 10:55 a.m. And then we finish our lecture at 11:30. Then we start our so-called lab, right? I see you in roughly 15 minutes, 14 minutes from now, 13 minutes now, it's 10:42. See you then, bye-bye. See you in 15 minutes. Okay, I'm back here. So let's just summarize what we did here so far. Summary. No. 1. Using Maxwell's equations, we proved that the electric and magnetic.
Professor, your video is off.
Oh, yeah. Thank you. Sharing the screen, right? So here you go. Using Maxwell's equations, we proved that electric and magnetic fields obey the wave equation. We also proved that the E and B are perpendicular to each other in vacuum. Okay. Then what we did next, we wrote E and B in terms of a plane wave. Okay. Here we are assuming, we assumed that the amplitude of these E and B waves do not decay. We did that for simplicity. For simplicity, we assume that the amplitude of this B and B do not decay. Okay. In reality, these electromagnetic waves, they do decay as the distance increases. Gold is the inverse of the square of the distance. Okay. What else we did? We found a relationship between the amplitude of the electric and magnetic fields, right? Magnetic fields. There you go, and the relationship is this one right in here. What else can we do? What else can we do? Okay, we are going now. Now we are going to calculate the energy density of a wave, of an electromagnetic EM wave. Okay. Using the results of electrostatic and magnetostatic. Do you remember? Just recall the equation for the energy density of the electric of an electric and magnetic fields. Okay, do you remember the equation? Here you go. I'm going to refresh your memory. It's not difficult to memorize. Okay, the energy density of the electric field, which by the way, delta U over delta V, which by the way is, I'm going to write that delta U of the electric field, right? Over delta V. Okay, yeah, let's keep this way. It's gonna be what? Half epsilon. Epsilon naught, remember that? What else? Electric field squared. And remember that? It's not difficult. This equation is very easy to memorize, right? We have something similar for the magnetic field. We derived that in our electricity and magnetism course. Okay, is proportional to the square of the magnetic field, but it's not going to be epsilon naught. It's going to be a different constant. It's going to be the magnetic permeability constant. Here you go. It's like that. Okay. So the first question we asked, how these two energy densities compare? Okay. That's the first question we asked. Let's see. Well, we can find that out just by applying this relation that we got here. Okay. So here you go. I'm going to here write my energy density due to the magnetic field right here. Go. It's going to be E divided by C. Okay. That's the amplitude. Yeah, let's see. And let's see how they compare. Here you go. Well, because the amplitude of the magnetic field is the amplitude of the electric field divided by a very large number, which is the speed of the light, we would suspect, right, that the energy density for the magnetic field is much less than energy density for the electric field. Is that true, right? You go, because of the above relation, we would suspect that the energy density of the magnetic field is much less than the energy density of the electric field. The question is that true? Is that true? Let's see if that's true or not. All you have to do is to replace this relationship right here in the equation for the magnetic field, in the equation for the energy density of the magnetic field, right? So let's see what we get by doing that. We're gonna get a C square here as well. And let's go another step, right? What this guy is? This guy is mu naught times epsilon naught. Mu naught times epsilon naught. Okay, that's what we're getting here. And let's see what's going to be the next step. Okay, so look what happened. You know, that suspicion of ours proved to be incorrect. Instead, we found out that the energy density of the magnetic field is the same as the energy density of the electric field. So an electromagnetic wave, we can conclude, right? An electromagnetic wave has an energy density that is given by, you know, so note C that our assumption proved to be false, right? In reality, the energy density in the magnetic field is the same as the energy density in the electric field. So now an electromagnetic wave has an energy density that's going to be given by, here you go. U equal to UE plus UB, right? Plus UB, which by the way is equal to twice UE, or epsilon naught E squared. And now that so electromagnetic wave has energy, and if we are smart enough, we can tap into this energy to use it for something useful, just like we do with solar panels, right? Solar panels are machines, are devices, are engines to convert electromagnetic energy into some other type of energy, like electrical energy. Okay, and plants do that too. Plants are just like solar panels, right? We poor human beings, we just invented artificial solar panels only now, whereas Mother Nature invented solar panels billions of years ago, right? And plants, you know, trees are just like that. It's a type of organic solar panel. And now we should ask ourselves if, okay, so here you go. An electromagnetic wave energy that can be tapped into to produce, to do some useful work, right? Provided we're smart enough, provided we are smart enough to convert this energy. Okay. So the next question that we ask is, what about momentum? What about momentum? There's an electromagnetic wave also has momentum. Has momentum as well. Right? It has energy. Does it also has momentum? Well, yes, we just found out that the electromagnetic wave has momentum as well. The answer is yes. Yes. And by the way, I looked here at Wikipedia. See that we have a nice article on Wikipedia about radiation pressure, okay? This idea of radiation pressure has been around for a long time. Remember Johannes Kepler? Back in 1619, he put forward the concept of radiation pressure, which is related to momentum of electromagnetic wave. Let me see if they have a momentum of, we were talking about radiation pressure here, but let's see specific momentum of electromagnetic wave. Doesn't look like they have it. Yeah, they don't have it. Does not exist, yeah. But they do have radiation pressure, which is related to electromagnetic, momentum of electromagnetic radiation, okay? Momentum of the electromagnetic radiation. So here you go. The idea of radiation pressure, which is related to momentum, right, of radiation, has been around since 1619. Johannes Kepler himself, he proposed the idea of radiation pressure just by observing the tail of a comet. You observe the tail of a comet always points away from the sun. So he starts thinking, is it possible that the light rays of the sun is exerting a pressure on those particles of the comet? That's why the tail of the comet points away from the sun. He didn't prove it mathematically. He didn't went through the whole derivation, right? Instead, it took 200 years for James Clerk Maxwell, again, James Clerk Maxwell, to assert that electromagnetic radiation has the property of momentum. And because it has momentum, it does exert pressure upon any surface that's exposed. Okay? So using his equations, he was able to prove that. So it took 200 and almost 250 years from Kepler, right? From the proposal based on experimental evidence, based on observation, that there was some sort of pressure. And then Maxwell proved that with his equation. And then he got the whole story, right? You initially propose it because you believe that something like that might be true due to your experience. Then someone else comes along, proves mathematically that it is exactly that, just like happened to Hertz, right? Faraday proposed that there was electromagnetic waves. He believes he had this intuitive belief. Maxwell proved mathematically that there exist electromagnetic waves, and Hertz demonstrated experimentally the existence of electromagnetic wave with an experiment. Here we have a similar story with different characters. Johann Kepler proposed the idea of radiation pressure. James Clerk Maxwell proved mathematically, almost 250 years later, that there is something called radiation pressure, but he didn't demonstrate experimentally. It took someone else to prove experimentally, the physicist Piotr Lebedev in 1900, almost 40 years later. Okay. And also there were other scientists here, right? Ernest Nichols is American. No, the Russian preceded him, and this guy here is a Canadian American. Most likely those two work together. The pressure is very small, but it can be detected. Okay? The pressure is very small, it can be detected. And people are proposing solar cells out there. You know, a spacecraft that propelled by the radiation pressure of the sun, for instance, or even the radiation pressure of lasers. There has been proposals like that. And not just proposals, but people demonstrated in practice as well. When I was there at NASA, there was a group of scientists that I was interacting with, and they managed to deploy their own solar cell in space. Okay. What's the theory? Okay, there's a theory behind that, but this theory is a little bit complicated. Okay, I'm not going to go through that. The book has some of the details, but I don't think the book explained it well. The best way to understand, you know, radiation momentum of an electromagnetic wave, the best way to understand momentum due to an electromagnetic wave is through, but best way, I mean, the easiest, okay? Best way is easiest. And we are going to cover that. Maxwell proved that using electricity and magnetism, okay? But there is an easier way to prove that. Is through special relativity theory. Okay? Einstein demonstrated that, and we're going to cover that. We're going to derive that in the class when we start covering special relativity. Okay, the two ways, right? Two ways of proving mathematically of radiation pressure or momentum of the electromagnetic wave. One way is through the Poynting vector. Okay, we're going to talk about that too. But I don't like this way. I think, and Maxwell derived that. I think that the best way is through relativity, simpler relativity theory. Einstein has proven that the momentum of a particle, of any particle, is given by this equation, okay? This U that you see there is the energy, the potential energy. Let me see if I get it right. That's CU. U is the energy of the wave, and then we have the mass of the particle. Let me see if I can find that. Relativity. There's a term in there that doesn't matter for this case, but somewhere here, what really matters is the C square U square. Okay. CP. No. I'm doing all the way around. Here you go. Sorry, it's going to be like that. Yeah, I'm mixing that up. Like that. Here you go. U square, CP square, and let's see. Unfortunately, they don't have it here. Let me. And you can prove that mathematically using the postulates of relativity theory. Let's see if I can get it. Bear with me. Summary. Okay. Yeah, MC. Okay, here you go. I got it. MC is square. Do you remember that? MC square. You must have seen that over and over again, right? This equation. MC square. And that should be the rest mass. And by the way, this term here is squared. This whole term here is squared. Okay. Yeah. Okay, that's for any particle. That's the genetic equation for any particle. The best and easiest way to understand momentum is through a special relativity theory. Even though Maxwell proved that before Einstein came along. Prove that with electromagnetic theory. Proved that with electromagnetic theory before Einstein came along, right? If a particle, if a particle is at rest, a particle of a given mass is at rest, this term is zero, right? And then you get the Einstein's famous equation E equal to mc squared. Here would be the rest mass. Okay? If a particle is at rest, the above equation reduces to Einstein's famous result. U equal energy, right? We're talking when I'm using U for energy because I don't want to mix that up with the electric field, okay? MC squared. The M in the C square is in reality the rest mass of the object. Okay. But we are talking about electromagnetic radiation. We are not talking about particles. We're not talking about particles. Okay, electromagnetic radiation has no mass whatsoever. No mass whatsoever. Okay. the electromagnetic radiation is due to a massless particle that we call the photon. So the above equation reduces to the other side of Einstein's result. This term is zero because electromagnetic radiation has no mass whatsoever, and the energy of a given photon can be written as Cp, where P is the momentum of the photon. P is the momentum of the photon equal to the energy divided by the speed of the light. Okay. Lowercase c. Okay. So electromagnetic radiation has both energy and momentum. Just like any particle out there, right? Particles out there also has energy and momentum. Okay, what else can we talk about? Remember that force can be written down in terms of delta P over delta T, right? So if your electromagnetic radiation has momentum, then it can also apply a force. And by the way, this is a very hot topic of research, okay? People have been using, lately, people have been using light beams to move particles around. It's what we call electromagnetic tweezers, okay? Light tweezers, photon tweezers. It's possible to move particles around using using a light beam. So if you somehow you can come up with a way to change the momentum of your electromagnetic wave, you will be able to apply a force and consequently a pressure, right? Remember that pressure, what's the relationship between pressure and force? Pressure is what? Oh, I don't hate that. I want the italicized, here you go, better. Okay, pressure is nothing but delta F. Delta F over, let's put it, actually it's force over area, better like that. Let's put it this way, here you go. Okay, force over area. And how can we change the momentum of the light? Okay, so the question is how can, if you can change, so if you can change the momentum of the light, if you can change the momentum of an electromagnetic radiation, right? Not just light, but electromagnetic radiation in general, you can apply a force to an object. And pressure as well. And pressure as well. So one way to change the momentum of electromagnetic radiation, one way, is by getting a mirror. Think about light. Light incident in a mirror. Light propagating toward the mirror has momentum in one direction. The moment that the mirror reflects the light, the momentum of the radiation changes. Make sense? Okay. One practical way to change the momentum of electromagnetic radiation, we use a mirror. Such a simple, such a simple idea, right? You can get a mirror out there, so you can shine your laser light in the mirror, and that mirror will suffer a force. You don't feel the force because this force is very small. Okay. Here on the surface of the Earth, there's no much practical way of measuring this force. It's very difficult. Only recently people start doing that in the lab. But in space, that can be more easily seen. Because they're in space, we do not have drag, we do not have weight, right? Your objects are weightless. And so it's easier to observe that in space. Okay. What time is that? 11:30. Okay, so we go. So if you use a mirror, with the light being incident under a normal angle, okay, we are going to have a change of momentum that is given by, here you go, delta P, right? Let's get the delta P. Here you go, delta P right here. Delta P is going to be P final minus P initial. Oh. So let's say P final is to the left and P initial is to the right, right? 100% reflective surface. So let's say so what you're going to end up having is going to be a change in momentum that's going to be equal to 2p minus 2p. Okay, in the x direction. You can even put it here as a vector. Go. Right, final. Oh no, I don't like it. Here you go. The arrow goes elsewhere, right here. Here you go. Right place. Put the arrow. Here you go. And then we put the hat. Here you go. That's all your delta P is. And now you substitute right here, you get a force, right? You get a force, but it's a force in the light wave. Okay, so let me do a drawing here. 11:30 already. Let's you got the idea, right? We didn't get everything yet in this chapter, but at least you got, let me just do a drawing here. I think I have, is that the one? I can use this one here. This one here. I think I'm gonna use this one here. Yeah, let me use this one here. Electromagnetic radiation right here. Photon, here's a mirror, right? I'm gonna photon going from the left to the right. I don't need this line. I don't need this line. Here you go. Oh, even better, I'm gonna put my x-axis here. make it thicker to look nicer. Okay, I'm gonna label the axis X. Photon with a momentum P towards the right, incident in the mirror. Okay, and then this photon is reflected. There is no loss. Also, is an ideal mirror. The mirror is 100% reflective. Yeah, here you go. Photon being reflected. Okay. Photon being reflected. Photon being reflected by a surface, 100% reflective surface. Reflective surface. Changing momentum is minus 2p. Okay. And now that you have this changing moment, you can have a force applied to the photon. But because of Newton's third law of motion, action and reaction, if the photon is if the mirror is applying a force to the left in the photon, it means that the photon is applying a force to the right in the mirror. Okay. So if a force is being applied to the left on the photon, it means that the photon is applying a force towards the right in the mirror. So that's the idea of radiation pressure, radiation force, and momentum of electromagnetic radiation. Okay, so there is one more thing that we have to do. We're going to do next time is going to be the pointing vector, and then we can move forward with other things. Pointing vector. That's the last thing that we are going to do for electromagnetic radiation. Any questions about that? It's 11:34 right now. We're going to have our 30-minute break for lunch. 30 minutes break for lunch. We're going to be back at 12:05 p.m. for the next lab. Okay, if you don't have any questions, we can stop now. And I see you in half an hour. See you. Bye-bye. So here you go. Let's take a look at our syllabus. Okay, so let's do this standing wave experiment, virtual experiment. We are almost done with electromagnetic waves. Okay, we're going to do a little bit more next time. Then I'm going to get into optics, geometrical optics. Relativity is going to be a little bit further down the way. Okay, so already introduced one of the possible results of relativity. And let's take a look at the data that we have for today. Let's see here. Let me see here. Looks like I got the lab 4. 1. Okay. So MG. Okay, so I need you to do the following. I misnumbered this lab. So what you're going to see there is labeled as lab number 5. I want you to renumber it as
Professor,
lab number 3, okay?
you were sharing your screen.
Yeah, I'm going to share the screen. Hang in there. Okay, so let's start. Let me first get the Google Drive. Go to Drive. Let us share the screen now. Summer group folder. Okay, I want, please renumber it to lab number 3. Okay, I'm uploading it at lab number 5. Number 3. Let's make sure before I upload that, make sure everything is right here. Oh, come on, man. Okay, one. Okay, that looks good. I'm fine. Okay, let's see, group 3. Okay, that's great. Group 5. Yeah, the idea is the same here. You have to work on the, I want to explain how the experiment goes as well. And you have to work out the units and all that stuff in the graphs. Good. Okay, that's good. Close it. Anything else? No, 3, right? Let's go for 4. 5, 6, 7, and 8. Wait 1 and 5. Lab notes. There we go. 16 CL, 21st, 22nd was the exam. Today is the 23rd. Let's see, this one is not the one we're doing. This is going to be the springs. Springs in series and parallel. We're not doing this one. Let's see, what about this one? Yeah, download your lab report. What's your Google Drive? Okay, that's another one for the spring, speed of the sound. Okay, we're not gonna do that yet. If you have time, we do it. So, okay, let's do the spring, huh? Let's see. Okay, this one here, this one. Huh. Yeah, here you go. '22 physical pendulum. Okay, should go right in here. Today is the 23rd, 22, standing wave 1. Okay, but before we get into the experiment, let's don't forget, make sure you upload the lab report, upload the report for lab 1, right? Most likely you already have done that. And what else? Check for P39 L. Did I put 05 there or did I put 5? Let's see. Yeah, 05. L05 group number, right? I'll put that Excel and rename it to P39 L03 group number, whatever group number you have. Okay, so that's the first thing you gotta do. Lab number 5, are we going in order? It's gonna be, I want you to rename it. Okay, to lab number 3. Okay, it's written there as lab number 5, rename it to lab number 03. Okay, and what we're gonna do, here you go, lab number 3, standing waves. Standing waves 1. And what we're going to do, let's get the lab again. Number 3. What are we going to do? What did we do in this lab, right? Here's the data. So what we are doing in this lab is to change the tension in the string. Let me see if I can get the, let's see here. Let's see if I have the illustrations, P39, no. P38, looks like I have to do the illustration from scratch. Yeah, I have to do illustration from scratch. 06 illustration. Yeah, unfortunately, I have to do that from scratch. I have some illustrations out there, but I just cannot find it. And so it's about a wave. Okay, propagation of waves in a string. Okay, in a medium, propagation of wave in a medium. The medium that we are using is a string. This one right in here. Can generate a wave the string by moving string up and down with your hand or any other device. Any other device, you know. If you look, for instance, if you look in YouTube, one nice way to do that is just get a speaker, okay, and attach and drive the speaker with a function generator. The generator is a standard equipment in any electronic lab. We have a bunch of those devices there at LA Harbor. Okay, so you know, that's one way to do that. Connect the speaker to a function generator, and when you do that, you can change the vibration of the speaker. The function generator frequency can be adjusted accordingly. In the process of adjusting the frequency, you're going to hear different sounds, right? That's one way to do that. Everybody here is familiar with the speaker. Maybe not everybody is familiar with the function generator, but that's what function generators do. Function generators, you know, provide a current in a given frequency. It's just these function generators are just a combination of capacitors with inductors. Okay. Okay, I'm gonna erase this one here. Okay, a wave needs to have a source of vibration. Use a source of vibration to generate a wave. A given vibrating source has amplitude, and frequency, or period. Okay. So, since the vibrating source generates a wave also has amplitude, frequency, and more, right? I mentioned that in the class. And this more is going to be what? It's going to be the wavelengths. Everything else is going to be a combination of those three. And I'm going to put here of those three parameters and wavelengths. Amplitude, frequency, and wavelengths. Velocity is going to be a function of wavelengths and frequency. Period, wavelength and frequency, and period is a function of the frequency as well. Here's the genetic equation for the velocity. Okay, but for a specific type of medium, the velocity for a specific type of waves propagating in different mediums, the velocity can be written in another way as well. Like electromagnetic wave, here you go, square root of the epsilon naught and mu naught. Okay. If the wave is not a vacuum, you write that down in terms of epsilon and mu. But we are concerned about a wave in a string. The velocity for a wave in the string is going to be the square root of the tension divided by the linear mass density. Going back to your data, okay, the tension in the string is dictated by this column. How do you control the tension? Oh, all you gotta do is to put a mass at the end of the string. Okay, I have an illustration here for you. Here you go. Here you go. That's how the whole thing works. We use a vibrating fork that at LA Harbor. There are other ways to do that. You can use a speaker as well. Okay. We attach our spring to a vibrating fork, to a vibrating source. Okay. The string passes through a pulley, and we hang our mass at the end of the string. The wave is generated right in here in this region. The tension in the string is going to be given by the mass times the acceleration of gravity. Okay. Makes sense? Okay, what else do you have to know? Okay, so we have, okay, this guy here, this is the mu, right? This is the mass per unit of length of the string. What you're going to do, you are going to measure the mass of this string. You are going to measure the length of this string. Going back to our spreadsheet. Okay, here's the mass of the string. It's a very low mass. Okay, the very low mass. We look at the value. 1, 2, 3 was 1 gram. And that's the total length of the string. 2.5 meters approximately for this case. And it's this one here is the vibrating length of the string. The vibrating length of the string is less than the length of the string. You use the M and L to find the mu. Okay, so let's go through the whole instrument, equipment, right? Here you go, going down. I'm going to go. So equipment. One, equipment and materials, equipment and materials. String of length L. Okay. Need a meter stick to measure L. Okay, resolution of the meter stick is what? 1 millimeter, which we can write that down as 0.001 meters. And the length should be written in this way. SI. String of length L, right? Scale. Okay. Measures the mass of the string and the hanging mass. The scale that we usually uses has a resolution of 0.01 grams, which is 0.00001 kilograms, right? 1, 2, 3, 4. Good. Yeah. Scale. So you know what the resolution of the mass, right? So you go ahead and put there the right number of significant figures. I'm going to put another measurement here. Length of the vibrating string is L prime. Just like before, the resolution, this measurement should be written like that for L prime. Okay, we use a strobe scope, strobe light. Everybody's familiar with those strobe lights, right? A very bright flash of light at a given frequency. We have those at the college. Strobe light to determine the vibration frequency of the tuning, the vibrating fork. Vibrating fork. Okay. What else? Here you go. So I had to put the vibrating fork here. Vibrating fork. Vibrating source to produce a wave in the string. Okay, and it's just like what I said. It looks like it's a fork with two prongs, right? That vibrate, that's connected to the electricity and vibrates at the frequency of the power line. This frequency, this frequency we can measure with the strobe light that we have there, the color that, and the strobe light, we can adjust the frequency of the strobe light. That's one way of doing that. What else? Pulley. All right, the pulley. Did I write down the hanging mass already? No scale, measured, okay. Hanging mass M, okay, of the string, comma, lowercase m, and hanging mass, big M. Hanging mass M is used to apply a tension in the string. So that's how you control. So what we're going to do, we're going to verify this formula that you see right in here. Let's see, that you see right in here. Okay, the velocity of the wave is the tension divided by mass per unit mass of the string per unit length. The tension in the string is mg. The mass per unit length is lowercase m divided by L, and that's going to be the velocity. Okay, so here you go. I have lambda. You will need to measure the wavelength of the string as well. Recall that the equation for a standing wave. What you're going to do, you're going to generate a standing wave here for different masses, for different tensions. Okay, you change the tension here in the wave, you create, the wave start propagating with different velocity, and in the process you also change the wavelengths. The frequency doesn't change because you're using the frequency of the power line, around 60 hertz. When you measure with the strobe, it's more like 54 hertz. Okay, around 54 hertz here. And because what we are producing here is a standing wave, we know that the length of the vibrating string, the wavelength of the vibrating string is going to depend on the tension, and also depends on the type of mode that excited. You can have a mode of 1 lambda over 2, 2 lambda over 2, right? Equal to the vibrating, and so on. So what we are going to do, we're going to change the tension by generating different modes of vibration. N equal to 1, 2. I'm going to put that in the regular format. This one doesn't require sequence figures, right? It's written here in N. See, we're going to generate different low modes of vibration by choosing a proper weight. Okay. The length is not going to change. Vibrating length is going to be always the same. The mass of the string doesn't change. Okay, all of those remain constant. What's going to change is this one here. That's going to control the mode that's vibrating for a given length. And you will be able to measure the wavelength. Very important to note, okay? Only certain weights, only certain values of tension will generate a mode of vibration. You're not, if you get a mass between this one, 2.25 kilograms and 0.62 kilograms, you are not going to be able to excite a mode, a standing wave. Okay? You have to get exactly those two values for this given lengths and mass density. Make sense? Okay, so, and then what do we have to do? What else do we have to do? We're gonna have a graph. Okay, here you go. Here's my equation. Here's the wavelengths, 2L prime over N, right? V velocity is equal to that, but velocity is also equal to that. The wavelength is going to be equal to 2L prime over N. This is an experiment. This is a measurement. This is a measurement. This is, everything in red is a measurement. Here you go, the equation that we have. Okay, I'm going to square both sides of the equation to eliminate this square root. Solve for mg. When I solve for mg, we get this equation right in here. And then what else? See, we get this relation. Okay. The frequency is the same. The length is the same. The vibrating length is the same. M over L is the same. What's changing here is this big M and the N. So what you're going to do? You are going to plot mg in the y-axis and 1 divided by n squared in the x-axis, just like we have here. Here you go. Mg, y-axis, 1 divided by n squared in the x-axis. You are supposed to get a straight line. You go ahead, write down the number of data points, the regression equation, R squared, find your CL, right? That's the theoretical value of your slope. I programmed the theoretical value of 4L prime. Here you go. 4L prime, right? Oh, sorry. I changed the equation here. The slope right here. H6. Okay, that's 4F squared. G6 squared is the L prime, right? 4F squared, L prime squared. And the mu, here's the mu. That's the result that you're supposed to get. Okay, don't forget to, this one. Yeah, I marked as a red, so don't worry about the significant digits. Let me put that in the numeric format. Should be around 16.66. Don't forget to put the units here. This slope should be close to this value. Is that clear? So let's start. So don't forget, I'm going to repeat here. Let's see. Upload the report for lab 2-1, right? And here you go. Check for P39L05G group number in your group folder and rename it P39L03, not 05. I have the wrong number in there. Okay, download the spreadsheet. Okay, so let's see if everybody's here. Attendance, lab. Today is the 23rd. Here's the exam 1. Exam 1. Brian Espino, are you there? Brian disappeared. Huh? Toby, are you there, Toby? Hey, Toby, you're listed here. Looks like you're away from your computer. You want to put a star here. Pedro Flores, are you there? Okay, Pedro is here. Lawrence Flores.
Here, Prof.
Okay, Kenny Villagomez.
Yeah, I'm here, Professor.
Thank you. Nolan Williams,
Here.
Harun Atif,
Here.
good. Musa, are you there, Musa? Okay, next is Daniel Nwagbo,
Yeah.
David Nwagbo, Zachary Blue,
I'm here.
good. Elena Boshard, go, good. Luis Cristo, what happened to Cristo?
I'm here.
Oh, you're there, okay, good. David, is that Maes, right? David, are you there? Okay, I don't hear you, Dave. I'm gonna put a star here. Robert Faust. Daniel Frady.
Here.
Okay, Olivia Kroger.
I'm here.
Next is Chuck Lu,
Here.
Amalia Gale.
Here, Professor.
Okay, Tiffany Wong. Tiffany's here, okay. Okay, that's Dave, right? Anthony Lopez. Okay, next, Shah Safi.
Here.
Next is Daniel Young. Ryan McNeil. Are you there, Ryan? I see Ryan listed. Oh yeah, here you go. I got it. Thank you. Claire Ottinger
Here.
and George Risk. George, are you there? Okay, if you're there, I don't hear you. I'm going to, I don't see in the list either. Mark 0. Jennifer Ramirez. Next is Noah Raymond.
Here, Professor.
Thank you. Natalie Santiago.
Here.
Mengshu Vang. Nathan Silva. Next is Sarina Lobana. Good. Alexis Nigret.
Here.
Okay. Danis Simon. Good. Thank you. Olivia Song. Olivia. I don't see Olivia here. And Keys, so I don't see Keys either here, right? Now let's see how many students we have. Okay, 31, I have 33. Okay, the student that didn't answer was Toby. Toby, are you there? I don't see you here in the list, Toby. Okay. I don't hear you saying anything, but you are here in the list. Okay, so let's do this experiment. This activity, no, not experiment, but activity. Any questions so far? 1241. Let me see one by one. Download. All right. Bobby, are you there? Okay, Pedro, did you download the spreadsheet? Pedro Flores. Okay, did you change the name to L03? Okay, good, thank you. Lawrence, did you do the same? Did you download it and change the name?
Yes, sir.
P39 L03, right? Kenny Villagomez.
Yes, sir.
Okay, Nolan Williams.
Yeah.
Good. Harun Atif.
Yep.
You did that, both of them? Download and change the name. Musa. Hi, Musa. I don't hear him. I'm gonna put a question mark here. So Daniel Nwapu.
Oh, yeah.
Okay, so download and change the name P39 from P39L05 to P39L03 group number, right? David Nwagbu. Yes, okay, both of them. Zachary Blue.
Professor,
Yeah.
this is Toby. I had to go grab something real quick.
Okay, okay. So what did you say? You had
I
what?
have to, well, I said I had to. I stepped out to get something. That's why.
Okay. Okay, good. Did you download the spreadsheet, Toby?
Yeah.
Okay. And did you change the name as well of the spreadsheet?
I'll change it right now.
Okay. Musa, I didn't hear from Musa. Okay, yes, you did. Okay, good. I got it. Zachary. Two things, right? Download
Yes.
and change. Okay, Elena. Good. Luis Crystal.
I'm gonna do it afterwards.
Did you download it, Luis?
No, I haven't.
Yeah. Okay, so I'll put an N here. I'll get back to you. Dave Dimaes. Not yet. Okay. Got Robert Faust. Downloaded. Did you change the name? You not just download, you also have to change the name, right? From L05 to L03. I'm going to assume to that you did both. You go, Daniel Freddy.
Yes, I already did it.
Yeah, okay, good. Olivia.
Yeah, I did it.
Okay, Chuck. Chuck Lou.
Yeah, I've done it.
Okay, good. Amalia. Yeah.
I did it, Professor.
Thank you, Tiffany. Yeah, good. Anthony Lopez. Group number 5. Okay, Shah.
Yes, I downloaded and renamed it.
Okay, good. Thank you. Daniel Young. Daniel Young, good. Ryan McNeil. Okay, Claire.
Yeah.
Okay, George, you're not there, right? George. I don't see George. Okay. Jennifer. Okay, Noah.
Yes, I got it and changed the name.
Okay, good. Thank you. Natalie Santiago.
Yes.
Mengshu. Yes, good. Nathan. Not yet. Okay, gonna put an in here. Sarina. Okay, Alexis.
Downloaded and renamed.
Yeah, please. Okay, so last one and but not least, right? Here you go, Darnis. How do I pronounce your name? Okay, and let's go through the stats here. What else? First thing you're gonna plot the graph mg versus 1 divided by n squared. Okay. N is a integer number, so you don't have to worry about significant digits, right? To add Nathan's name, do I just put down? Okay, let me see. Nathan, yeah, you can put it here. Okay, yeah, put down here, right? One more, and just do not change the position of those tables, right? Okay, so so you highlight, right, this one and just drag to create a new line here. if you have the proper equipment, this type of setup can be used to create 12 different experiments. They always analyzing the thing carefully, and if you have everything right, if you can change the frequency of your tuning fork, you can create a total of 12 experimental activities, 12 different experimental activities, just by changing the length, the vibrating length, by changing the frequency, by using different strings of different linear mass densities, okay? Change the tension, right? Combine, mix and match, you end up getting like 12 different of those experiments. I managed to do only 4 of those for my students. 2 at the Harbor and 2 there at the California State University at Dominguez Hills. Well, 48. Let me know whenever you're done with the graph. The next step here would be to plot the graph. Attendance. Graph. Okay, I'll give you some time.
And Professor,
Yeah,
which one is on the x-axis again?
you go, going back here. P-Lab notes, here you go. Y-axis, X-axis.
Okay, thank you.
This one next to the other. Okay, right in here. Once you put the device to oscillate, you'll be able to see the node, the wave clearly, whether it's 1, 2, or 3, and then you can get your ruler or meter stick and measure the full wavelengths. Those are measurements, okay? Measurement. This is not a measurement. Here you're just counting. This is not a, no, you can say it's a measurement. It's a measurement without significant figures, okay? Measurement, result. Measurement with the scale, measurement with a meter stick, measurement with a meter stick, measurement with a strobe. Here's the result, and here's a result from a previous experiment. Okay. Okay, I'm gonna walk away momentarily from the computer here while you work. And I'll be back shortly.